Imagine a spaceship that can leave Earth and arrive at a distant star before the light from its launch even reaches it. Imagine traveling so fast that time itself seems to twist, where the line between cause and effect begins to blur. It sounds like science fiction, but it's actually science's greatest speed limit, the speed of light. For more than 100 years, Einstein's theory of relativity has stood like an unbreakable wall in front of us. No matter how much energy you pour into a rocket, no matter how powerful your engine is, if your ship has mass, you can only ever get closer to light speed, never past it. It's like chasing a horizon that keeps receding as you run. At 90% of light speed, time for you slows down dramatically, but the energy needed skyrockets. At 99.9999%, it becomes astronomical. And at 100% light speed itself, the required energy shoots up to infinity. In other words, the universe is saying, nice try, but no. And yet, the dream of faster-than-light travel refuses to die. Because if we could somehow cheat this limit, everything would change. The nearest stars wouldn't be distant anymore. The galaxy would shrink. And maybe, just maybe, the universe would reveal shortcuts we've never imagined. So the real question is light speed truly unbreakable, or just a very clever trap? To explore that, we need to venture into some of the strangest corners of modern physics, places where reality itself starts to bend. Before we talk about spaceships and warp drives, let's start with something even stranger: particles that might already live beyond light speed. Physicists have given them a name: tachyons. They're purely hypothetical. No one's ever seen one, measured one, or even found convincing evidence they exist. But mathematically, they could exist. And if they did, they'd flip a lot of what we know upside down. Here's the basic idea. Normal particles, like electrons or protons, have mass. The faster they move, the more energy it takes to keep accelerating them. And as Einstein showed, the closer you get to light speed, the more that energy requirement explodes. You can approach the limit, but never pass it. Tachyons would be the opposite. They're imagined to have imaginary mass. Yes, imaginary, as in involving the square root of -1. This strange property means they'd always move faster than light. And here's the wild part. If they somehow slowed down toward light speed, they'd need infinite energy to do so. For them, slowing down is impossible, in the same way speeding up past light is impossible for us. They live permanently in the superluminal zone beyond the cosmic speed limit. But this comes with a huge problem: causality, the principle that causes come before effects. If tachyons existed, they could theoretically send information backward in time. For example, imagine you send a tachyon message to a friend on another planet. Because it moves faster than light, it might arrive there before you even sent it from your perspective. Then, your friend could reply in a way that reaches you before your original message left. Congratulations, you've just created a causal paradox. The effect happened before the cause. Time becomes negotiable. This isn't just a quirky thought experiment. In relativity, faster-than-light signals automatically lead to the possibility of closed time loops, paths, where information travels into its own past. And if you can send messages to the past, then logically, you could send instructions that prevent the message from being sent in the first place. The universe, as far as we can tell, really hates that kind of thing. Most physicists believe this is why tachyons, if they exist at all, can't carry useful information. They'd either be unstable, or their interactions would be somehow hidden from the observable world. In short, tachyons are a fascinating mathematical idea, but if they were real, they'd mess with reality so badly that the universe would have to rewrite its own rules to stay consistent. So maybe breaking the light barrier by riding on imaginary particles isn't the way. But what if instead of beating light, we could make space itself do the hard work for us? For decades, science fiction has loved the idea of simply punching a button and zipping off to another star at warp speed. But surprisingly, this isn't entirely fantasy. In 1994, a Mexican physicist named Miguel Alcubierre did something incredible. He showed, at least on paper, that general relativity itself might allow a form of faster-than-light travel without technically breaking the speed of light. Here's the genius of his idea. Instead of trying to accelerate a spaceship through space faster than light, Alcubierre proposed we could move the space around the ship. Imagine space as a giant rubber sheet. Your ship sits on that sheet. Normally, to travel, you slide along it that's limited by light speed. But what if, instead, you compressed the sheet in front of you and stretched it behind you? The ship wouldn't be moving locally. It would just be riding a wave of distorted spacetime carried along effortlessly. In this warp bubble, the space in front of the ship contracts, bringing distant points closer. The space behind expands, pushing the ship forward. From outside, it might look like you're traveling faster than light. But inside, the ship isn't actually moving relative to the surrounding space. Locally, it's obeying all the rules. It's like standing still on a conveyor belt that's dragging space itself under your feet. This clever trick avoids the tachyon paradoxes because you're not really outrunning light through space, you're taking a shortcut by reshaping space itself. But, as always, there's a catch, and it's a big one. To create and sustain a warp bubble, Alcubierre's equations required exotic matter, a form of energy with negative density. Basically, you'd need to gather up enormous amounts of something that doesn't exist in any usable way. Estimates suggest the original Alcubierre drive would need more energy than the entire observable universe. Later refinements reduced that figure, but we're still talking about astronomical amounts of negative energy, something far beyond our current or foreseeable technology. And even if you somehow could build the warp bubble, there's another problem: controlling it. Alcubierre's model doesn't allow signals to escape from inside the bubble to its edge. That means you can't steer it from the inside. It's like being trapped in a runaway train with no brakes and no steering wheel. So, in theory, warp drives don't violate relativity. They work with it in a clever way. But in practice, they're still locked behind barriers of physics and engineering that make today's fastest rockets look like toy cars compared to a starship. Still, the Alcubierre drive is more than just a neat thought experiment. It shows us something profound. The speed of light might be a limit for movement through space, but maybe not for how space itself can behave. And that brings us to another equally mind-bending idea. What if instead of bending space into a wave, we could fold it? Imagine you've got a map of the galaxy printed on a sheet of paper. You want to travel from one star on the left side to another on the right. Normally, you'd trace a line across the paper, a long journey, bound by the speed of light. But what if, instead, you just folded the paper so the two stars touched and poked a hole straight through? That's the essence of a wormhole. In the language of physics, a wormhole, sometimes called an Einstein-Rosen bridge, is a tunnel through space-time. One end might be near Earth, the other could be light years away. Step through one mouth, and you could emerge on the other side almost instantly, no matter how far apart the 2 points are in normal space. The idea comes directly from general relativity. Einstein's equations don't just allow wormholes, they almost invite them. Spacetime isn't rigid. It can stretch, bend, and, in theory, even form bridges. If space can be warped into waves, like in the Alcubierre drive, then why not fold it into tunnels? But there are some serious catches. The simplest wormholes that appear in Einstein's math are not stable. They pinch off and collapse so fast that nothing, not even light, can pass through. They're like cosmic soap bubbles that pop the moment they form. For a wormhole to stay open long enough for a spaceship to travel through, you'd need to prop it open somehow. And just like with warp drives, this requires something exotic: negative energy. This is energy that behaves in the opposite way of normal matter, effectively pushing spacetime outward instead of pulling it in. In theory, a ring of negative energy around the wormhole's throat could counteract the natural collapse and keep the passage stable. This isn't pure science fiction. Quantum field theory, our best description of subatomic particles, actually allows for tiny amounts of negative energy to exist, at least temporarily. It happens in phenomena like the Casimir effect, where two metal plates placed extremely close together create a region of negative energy between them. The problem is, this happens on microscopic scales, not cosmic ones. We can make tiny negative energy blips in the lab, but building a stable wormhole big enough for a human, let alone a spaceship, is so far beyond our abilities that it's basically magic, for now. And then there's the time problem again. If you took one end of a wormhole, moved it near light speed for a while, and then brought it back, relativity says time at that end would have slowed down compared to the other. You'd effectively turn the wormhole into a time machine, allowing someone to enter one end and exit in the past at the other. Once again, causality, the bedrock of cause and effect, starts to wobble. Some physicists, like Stephen Hawking, argued that these kinds of paradoxes might trigger what he called chronology protection, some unknown physical mechanism that destroys time machines before they can cause trouble. In other words, the universe might self-correct to keep time consistent. So, wormholes are mathematically allowed. They might even exist naturally somewhere out there. But stabilizing, controlling, and surviving one? That's another story entirely. Still, wormholes show us something amazing. Even if the speed of light can't be broken locally, the universe itself might have built-in shortcuts, hidden paths, through the cosmic landscape that bypass the long road altogether. We've explored tachyons that might outrun light but break causality, warp bubbles that surf space-time, and wormholes that fold the universe like paper. Each of these ideas pushes at the edges of physics, teasing us with possibilities that sound impossible but aren't completely ruled out. So what would actually happen if we broke the speed of light? Well, first, we'd be rewriting one of the deepest rules of nature. Right now, light speed isn't just a number, it's a cosmic speed limit woven into the structure of reality. It's the speed at which cause leads to effect. It's the maximum speed that information can travel. It shapes how time flows, how space stretches, and even how energy behaves. If something could move faster than light, we'd have to rethink our entire understanding of space and time. The order of events could become subjective. What looks like before to one observer might look like after to another. In some frames of reference, signals could loop back and arrive before they were sent, opening the door to time paradoxes, self-contradictions, and timelines that simply don't make sense. Even our concept of distance would change. Right now, far away simply means it would take a long time for light to get there. If light speed wasn't a limit, the scale of the universe would collapse. Distant galaxies could become as accessible as neighboring planets. In principle, a civilization capable of superluminal travel could cross the galaxy in weeks or maybe days. Interstellar colonization, communication between stars, even escaping the heat death of the universe, it all becomes imaginable. But there's a catch. The laws of physics are stubborn. Every time we think we've found a loophole, reality quietly points out the fine print. Tachyons mess with causality. Warp drives need impossible energy. Wormholes demand negative energy on an unimaginable scale. And if any of these things do exist, the universe seems to hide them behind mechanisms that prevent paradoxes and violations of fundamental principles. Some physicists believe this isn't a coincidence, that the speed of light isn't just a limit. It's a protective boundary. It keeps the universe logically consistent. It ensures that cause precedes effect, that events unfold in a way that can make sense. Without it, reality might collapse into chaos. And yet, we keep looking, because that's what humans do. We stare at impossible walls and wonder if there's a door we can't see yet. History is full of limits that turned out not to be absolute. Heavier than air flight was once impossible. So was reaching space. Maybe one day, light speed will join that list. For now, though, light speed remains undefeated. It's not just a number, it's the rhythm of the cosmos, the ultimate reference point for everything that moves. But the moment we imagine surpassing it, we're reminded of just how strange, elegant, and fiercely protected our universe truly is.